Okay, so welcome everyone. It's my great pleasure to welcome you to the latest seminar from the Spatial ML seminar series. Thank you to Andrew for organising the series. It's been going really well, and we've had a number of really interesting speakers. Today, no exception, we've got Suhail Basalama, who's a fourth-year PhD student at the University of California, Los Angeles, UCLA, where he's advised by Professor Jason Kong, whose work is probably well known to most people in the field. Suhail's research has been focused on high-level synthesis for FPGAs, and he's been working on hardware acceleration for DNNs, for systolic arrays, data flow architecture optimization, and design space exploration and hardware compilation. So I'm really delighted to open the floor to you, Suhail, to tell us about your work.
Thanks for the introduction. And good morning or good afternoon or good evening for all of you. Today I'm going to talk about two of our works. One is called FlexCNN, an end-to-end framework for composing CNN accelerators on a FPGA. And the first part of the presentation and the second part will be about a comprehensive design space exploration framework for systolic arrays. So, and if you have any questions, please let me know or put them in the chat. I'll try to keep an eye on the chat. So first, for FlexCNN, we found that modern CNNs come with new challenges, and our work tries to tackle these three challenges. The first one is the computation to communication disparity within CNN layers of the same type, and we'll talk about each one in detail. The second one is handling various types of CNN layers, and especially, for example, transposed and dilated convolution layers. And the third challenge is the end-to-end integration with machine learning frameworks and CNN pipelines. The architecture of FlexCNN is a configurable and composable streaming data flow architecture that is used to implement a specific CNN. In this example, we have different modules for the different layers of the CNN. And the main computation engine is a systolic array to perform the convolution operations. And the other modules are lightweight, implemented using line buffers. And the architecture does not have to be this for all of the CNNs. It depends on what type of layers are found in a specific CNN, and then it will be run for, like, the whole CNN will be divided into small subgraphs that will be mapped to this architecture and processed sequentially. And it is runtime configurable through this lane called layer instruction, which will enable or disable one of these modules and have some control over how they execute. So, for example, one group of layers may contain depth-wise convolution. It may require ReLU and activation after that, and then the standard convolution, and then it could be followed by pooling but not upsampling. So this will be bypassed. So for the first challenge, the computation to communication ratio disparity within CNN layers refers to the arithmetic intensity, or the ratio between the amount of data and the amount of computation for specific layers. And this changes radically between the layers of a specific CNN due to the different dimensions of the input-output feature maps and the kernel sizes. So these are, for example, three different convolution layers from the famous CNNs. And the problem with having variable CTC is that we cannot sometimes have fully pipelined execution where we have some imbalance between the reading of the data from off-chip memory and the execution of the computation. And our solution to this is we use the concept of dynamic tiling, which is we use tiling factors that are configured during runtime to enable more balanced execution. And also we have some data layout optimization to enable maximizing the burst length when reading data from off-chip memory. So, for example, for a given group of layers, for example, if we use a set of tiling factors called tiling factors 1, the execution may look something like this, where single block is a tile of data. And you notice here that reading the input feature maps and the output feature and writing the output feature maps takes much longer time compared to the computation and the reading of the weights. But another set of tiling factors can lead to more balanced execution. And we show that, for example, for this CNN called OpenPose for pose estimation, the first 24 layers, we see that the performance, the attainable performance between uniform tiling factor for all the layers compared to this dynamic tiling, which is customized for each layer. These are the blue dots here, and then the uniform tiling in the red dots. And then for this CNN, we found that the performance can be up to 6 times better using dynamic tiling, and the data layout optimization maximizes the effective DRAM bandwidth from like 4 gigabytes per second to around 12 gigabytes per second. Also, the computation to communication ratio increases. And the second challenge is the how we handle various types of CNN layers. This is an example network called ENET used for image segmentation, for real-time image segmentation. It has 209 layers, including 78 normal convolution layers, 8 dilated convolution layers, and 8 transposed convolution layers. I'll describe what these, if some people haven't heard about them. These dilated and transposed convolution are variations of the normal convolution used usually in segmentation. So the block, as you can see, has various types of convolution. Here we have normal convolution with 3x3 kernels. Here we have asymmetric convolution with the kernels being like not square kernels. And here we have dilated convolution with different dilation factors. Also, we have transposed convolution. So now the challenge is, how can we handle all these types of layers? So we try to divide the type of layers of a CNN into 2 types: the computation-intensive layers, which require a lot of DSPs, like these normal, transposed, and dilated convolution layers, and then the non-compute intensive layers, like pooling, upsampling, and the other layers. So our approach is we have a versatile systolic array for compute-intensive layers. This systolic array will be able to handle and accelerate different types of convolution within the same systolic array. And then we have dedicated hardware modules for the non-compute-intensive layers. So transposed convolution is also called fractionally strided convolution, is an upsampling layer that uses trained weights to produce high-resolution feature maps. And the naive implementation of transposed convolution inserts a lot of zeros in the input feature maps, as shown in this picture. So the original input feature map is just these zeros, the padding zeros, and then 1, 2, 3, 4. But to perform the transpose convolution, we need to reverse the kernel. So it starts 9, 8, 7, 6, 5, 4, 3, 2, 1. And then we perform normal convolution on this expanded feature map with zeros. But as you can see, this can lead to a lot of underutilization of computation resources because of all these zeros. And then the second one is the Atraus or dialectic convolution, which maintains the resolution of coverage of the feature maps by expanding the receptive fields of the filters. So for example, if we have a 2x2 filter, we can expand it into 3x3 by inserting these zeros to cover more area of the feature maps. And this also results in a lot of redundant zeros. So our approach is we use the decomposition of the filters, converting the problem into normal convolution for transpose convolution. So if this is the original transpose convolution or the naive approach, what we do is we decompose it based on the patterns of the sliding window. So for example, when the sliding window is at this position, we only need the 4 edges of this filter. So the filter will be the 9, 7, 3, 1. When the kernel is at this location, you see that only the middle up and middle bottom of the filter is needed, which is the 8-2. When it's in this location, we will need the left and right. And then when it's at this location, we will need just the one in the middle. This decomposition approach does not require the redundant zeros we use for the naive approach, and reduces the number of MAC operations a lot. And the ideal speedup, or the ratio between the original naive approach and this decomposition approach, is close to the squared of the stride, the transpose convolution stride. Oh, someone asked, what is CTC? CTC is computation to communication ratio. Okay, so the stride for transpose convolution is the number of zeros we insert between the pixels of the input feature maps. So the ideal speedup is this stride squared. Similarly, for dialectic convolution, we also do a decomposition of the filter. Sorry, we do a decomposition of the input feature maps. So in the same approach, when the filter is in the first position, we use these 4 pixels. In the second location, we will need these 4 pixels, and so on. And the ideal speedup for dialectic convolution is given by this formula, where D is the dilation factor, which is also the number of zeros we put in the kernels. So now that we have this decomposition approach, we can have 2 approaches. One is we can have a dedicated accelerator or systolic array for each type of convolution. But you see that the problem with this approach is we will need to divide the computation resources between these 3 types of convolution. But our approach is we have a unified versatile systolic array that can be dynamically configured during runtime to either perform normal convolution, transpose convolution, or dialectic convolution. We did that by customizing our systolic array by customizing the data paths to support this decomposition, and also by adding some control to each PE to perform these operations. And based on our evaluation, we found that for computation bound layers, we can achieve close to the ideal speedup for both transpose and dilated convolution, and not so on for the communication bound layers. And also the hardware resource overhead of adding these two types of convolution is not that much. We see around 7% increase in LUT utilization, 3% in flip-flops, and 3% DSP utilization. For the on-chip memory, HLS tool may choose to use BRAMs or URAMs. So you see here we have more BRAM utilization but less URAM. Here it's less BRAM but more URAM. And this will also depend on the design space exploration we use to find the parameters of the specific architecture. The last challenge is the end-to-end integration with the machine learning frameworks. We see that the CNN computation is the most computation intensive, but there is a lot of overhead from the other pre-processing and post-processing steps of CNN pipelines, which are usually overlooked in prior works. So our approach involves a two-step or two-level pipelining approach. The first one is a software level pipelining, where we create a pipeline that will overlap the execution of the pre-processing, inference, and post-processing steps similar to this diagram. And then for the hardware level pipelining, we will overlap the invocation of the kernel with the reading and writing of the data from off-chip memory to on-chip memory. And the impact of these two optimizations can be huge. For example, without any optimizations, just executing everything sequentially, we will get around 208 millisecond runtime, or around 4 frames per second. But then when we add the first pipeline optimization, we get around 10 frames per second. When we add the second pipeline, we get around 23 frames per second, which is an important optimization that people should consider while having end-to-end pipelines. And FlexCNN has multiple components. The first one is the CNN layer mapping, which will take the list of modules and the topology of the architecture, and then it will take the CNN in the Onyx format and tries to map the CNN and break it into a small group of layers that will be mapped at for each run of the architecture. We call these layer bundles. So a layer bundle may contain like convolution followed by batch normalization or activation. So we don't want to have these as separate runs because we want to minimize the off-chip memory communication. And we would like to have this represents the layer fusion optimization, where we fuse the non-computation intensive layers with the convolution layers. And then the second step is, giving these layer bundles, we will do a design space exploration to find the optimal dynamic tiling factors, which will generate the control instructions. And then it will also find the hardware parameters for each of these modules we provided based on the target FPGA. Finally, we generate the design and the test bench to run on FPGA. And some of the optimizations, as we just mentioned, include layer fusion and layer parallelization, dynamic tiling, and then data layout optimization. And then we have the versatile systolic array to support all these types of convolution in one systolic array to maximize hardware resource reuse. And the design space exploration engine. So since all these hardware modules in FlexCNN are parameterizable to tune the computation and on-chip memory resources, we built an analytical model to estimate the performance and resource utilization. And the design space exploration will perform two-step search. The first one is we will generate all possible hardware parameters that can fit on this specific FPGA. And then for each candidate, we perform a greedy search, starting from the first group of layers to the end of the CNN to find the dynamic tiling factors. The dynamic tiling factors cannot be arbitrary. They need to be, there are some constraints, which is like between two groups of layers, they need to have at least one similar tiling factor so that we can read the data in the correct order for the next modules. And this greedy search gives us good results, but it may not be optimal all the time. Here is a more detailed evaluation of the versatile systolic array. So these are the problem sizes. For small problem sizes, they can be communication bound. So we don't have the expected ideal speed up compared like to 4x, we get even some slowdown due to the added overhead. But then once we go to the more computation intensive layers, we see that we can achieve close to the ideal speed ups, which are just the convolution without all these redundant zeros. Similarly, in the dilated convolution, we can also achieve these ideal speedups. The DSP efficiency is just the actual performance using the non-zero MAC operations divided by the peak performance of the systolic array. And finally, we implemented 3 CNNs. One is the open pose CNN used for position estimation. At the time of this paper, we didn't have any other works implementing this network on FPGA, so we just compared with GPU and CPU. And we have similar performance to the NVIDIA Tesla V100 GPU in terms of the throughput and latency. And then for the UNet is a famous CNN used for medical imaging and segmentation. We also compared it with CPU and GPU on 2 prior works. Although the prior works are using fixed 16-bit data types and fixed 8-bit data types. So the fixed 8-bit work achieved the highest performance, but our float 32-bit still achieves better performance than the 16-bit fixed point. For the ENet, we compared with the CPU and GPU with float 32-bit. We see that we can have the best performance compared to both CPU and GPU. And then we also compared with the Xilinx Vitis AI DPUs, or these DPUs are RTL designed optimized engines for deep learning applications. And the first one is optimized for high throughput. The second one is optimized for low latency. We see that the high throughput can achieve much better performance compared to our work. But in terms of the latency, we could not calculate the exact latency because this data was not available, but according to our calculations, it could be between 8 and 113 milliseconds, while our accelerator achieves just 66 milliseconds. And for the throughput, compared to the latency optimized one, we also have slightly better results. Okay. So the second part is our work on design space exploration for systolic arrays. So many of you are probably familiar with systolic arrays, but just a recap. A systolic array is just an array of processing elements that process data in a systolic manner, as shown in this figure. This will perform 3x3 matrix multiplication, and then each PE will represent one of the output data of the output matrix. So as we all know, systolic arrays, they have been used in multiple industry accelerators, for example, Google TPU and the Tesla self-driving chip and the Amazon Inferentia chip, because they offer parallelism and high energy efficiency, and they are very scalable. But the main challenge is the large design space and the number of optimizations that we can do. So for example, for 1024 by 1024 matrix multiplication, we can have like 6 data flow mappings, meaning that for the 3 loops of matrix multiplication, which loops we map to the space dimension and which loops we keep in the time dimension. These 3 systolic arrays, they are just using 1 dimension of the matrix multiplication to be mapped to the space dimension. So they are one-dimensional systolic arrays. These are 2-dimensional systolic arrays, but using different loops. So this is the first target. The second one is the number of loop permutations. So for a given data flow, we can have different loop permutations which can affect the off-chip data communication. So these have the same space-time mapping, but different loop permutations, and we can have different off-chip communication. And here we have like 3 loop permutations. But then lastly, as you see, this is the tiled implementation of matrix multiplication. And now we have 6 combinations of possible tiling factors that we need to find the appropriate values for each one of them. This leads to around 2 to the 40 design candidates. And how to search this huge design space is a challenging problem. So we can see that even in industry, it takes from few months to more than a year to optimize and tune systolic array design. So we found a few limitations in prior search methods. The first one is like an incomplete coverage of the design space, where some prior works will only consider the tiling factors that divide the problem size. And we found that this can result in around 40% performance loss. The second limitation is inefficient search methods or imperfect pruning heuristics. For example, some prior works will use off-chip traffic as a pruning heuristic, but it could miss optimal designs. And the last one is inaccurate performance modeling. So, for example, some prior works ignore the prologue and epilogue phases of the pipeline, which can lead to 9% performance loss. Okay, let's take the 1024 matrix multiplication. So some prior works will just use the divisors of the problem size. This may not be a problem for ASIC designs or where the resource, the computation resources are not limited. But we found that this is not necessarily true. So for example, if we found that for this problem size, the candidate we found is 4 by 32 systolic arrays, the next candidate would either double the number of rows or columns of this systolic array. And as you can see here, using divisor tiling factors can lead to the very next candidate will overutilize the FPGA resources and will not fit on the FPGA fabric. But the candidate just below that uses half of these resources, and this leads to wasted FPGA resources. So the best design should use non-divisor tiling factors to maximize the DSP utilization of the FPGA. So in this case, using only divisor tiling factors, the best design we found uses 5,120 DSPs, and the throughput is around 500 gigaflops per second. But this design that we found uses non-divisor tiling factors, and then the throughput is around 50% faster. Also, a common wisdom is to use off-chip communication as a pruning heuristic. But what we found is, for example, this design has the minimum off-chip DRAM traffic with around 16 megabyte of data. But the performance is much less than this design that has much more DRAM traffic, but also better performance. And the reason is the minimizing the off-chip traffic will require that we'll have like the problem when we do non-divisor tiling factors, we will need to pad the problem size with zeros, which will add more DRAM traffic. But this can be, but using the off-chip memory traffic as a criteria can miss these optimal designs and just use the 5,000 DSPs. The last one is like some prior works will only consider the computation phase of the accelerator as a performance model, but it could lead to like we try to simplify our performance model by eliminating the prolog and epilogue phases, but this led to 9% slower designs compared to using the more accurate performance model. So to explore this huge design space, we proposed two methods. The first one is a hybrid genetic mathematical programming method. So since we have an accurate performance model, it is difficult to solve with a mathematical programming solver. But we need to have an initial population for the genetic algorithm. So we use a simplified version of this performance model that takes the most important factors, the communication and computation, and we use the solution as an initial population, and then we use genetic algorithm to find and tune these tiling factors through the mutation and the other methods of the genetic algorithm to find the non-divisor tiling factors. And the second search method is a padding-based search algorithm. So when we use non-divisor tiling factors, we will need to pad the problem size with zeros so that we don't have complex hardware logic. So in this diagram, we show that the best performance we find for each padded problem size. So if we start with 32 by 32 problem size at this point, when we pad one dimension with zeros, we see that the overhead eventually will increase. The more padding we add will be more than the gain we get, but also some padding can lead to better tiling factors that can be better than the original problem size. So our algorithm would explore the design space in the direction of increasing these paddings on the I dimension, for example, and the J dimension. I will show an example how this algorithm works. So let's take the original 1024 by 1024 by 1024 matrix multiplication. And this is the original non-padded problem size. Let's say that the best performance we get is around 32 cycles. Now we add padding on the I dimension, and we see that the performance we found with this candidate is worse. So now for each of these new problem sizes, we will only search for divisor tiling factors, which is equivalent to searching for all non-divisor and divisor tiling factors of the problem. But instead, we are padding the problem size with zeros, and then we are performing the search with using only divisor tiling factors. So now when we do the padding on the I dimension, we get worse performance at this point. But then when the problem size is 1026 by 1024, we got some improvement. We continue the search, we got even better performance because this problem size allows for better tiling factors. And then we continue the search. We have a threshold on the I and J dimension. In this case, it's calculated using this formula. We just found this formula experimentally. And in this case, the threshold is 3. So if we couldn't find any better padded problem size after 3 consecutive problems, then we break. So eventually here, we didn't find any improvement. So now we pad the other dimension with 1 0 column, and we repeat the search. And we found here that we got even better performance at this problem size, and we continue the search until the algorithm terminates. Eventually, we see that the overhead of the zero padding exceeds the benefit of the tiling factors that we can get. And then the final padding would be the 1026 by 1025. And the minimum cycles is 26, and the dimensions of the systolic array is 9 by 25, which does not divide the original problem size, but can give us better performance. So first, to evaluate our genetic mathematical programming method, we compared it with random search, exhaustive search with pruning, simulated annealing, Bayesian optimization, and then with open tuner and reinforcement learning. We found that our genetic mathematical programming method achieves the highest sample efficiency, finding close to the optimal solutions in less than 3,000 design samples. And also the best designs found for each search method. We found also the genetic MP method achieves close to the optimal designs found by exhaustive search. But then there are some, so the genetic algorithm search can be much faster than the padding-based algorithm, but it can miss the optimal designs. The padding-based algorithm identifies the optimal designs for 15 out of the 16 problems whose exhaustive search is completed. So these problems have huge design space. These with the red bars, it's more than 200 billion points. But we found that our padding-based algorithm achieves close to the optimal performance while exploring much smaller design space. And the hybrid method is still within 11% of the optimal designs, but you can see that only using the divisors of the tiling of the problem size can be 60%, as low as 60% of the optimal performance. And on average, we have 187 reduction in the search space using the padding-based search algorithm compared to the exhaustive search, and around 64 x reduction in the search time. So for example, from 3.6 billion points, we only searched 28 million. And for even bigger problems, this one with 84 billion points, we only searched 360 million points, and we still found the same optimal solution with this search method. And finally, we evaluated found solutions of this search method on FPGA. So with the divisor only, for this problem size, we found this dimension of the systolic array and all the tiling factors, which gave us around 500 gigaflops per second. But then the best performance we found was with these dimensions, where we padded the problem to 1040 and 1032 with these number of columns and rows. And these designs are generated by our other compiler, O2SA, which takes a C code and generates a systolic array. But it requires the manual tuning of these tiling factors, the data flow designs, and the permutation. With our search algorithm, we can automatically find these parameters for the user to further automate the systolic array optimization. These are some of the references. And thank you, and let's hear if anyone have any questions.